All right. Project 1 results should start trickling back, the emphasis on trickling. Actually, it's really nice. The first 4 that I did they passed all the tests. That was pretty impressive. So we'll see. Things always get tough when you get to the ones that don't pass all the tests, but there you go. So now what I'm finding is, as you'll see in the comments that come back to you, is in general, the things that most struck my eye so far, but these were, of course, the ones that passed all the tests, were that there was some, I saw some issues of formatting or taste that that's sort of great. So, I mean, watch those Mongo procedures that you're generating particularly. When things get long, it's time to start getting suspicious. Very few procedures really have to be long. Or just think of it this way. A long procedure is one that has lots of little independent pieces that are just longing to get out of it, and it's best to let them out. And when your lines get long and all crowded together, I don't know whether you think that you're paying for these spaces or something, but you're not in general. So a little more attention to these matters of appearance would help make code look quite a bit more professional, I think. So anyway, you'll be getting other comments, and we'll see when I start encountering the submissions that had problems, then perhaps I'll have other things to say. Now, on the subject of testing, I in general try to avoid counting in your favor tests that you have imported from the AutoGrader. So don't rely on the AutoGrader, please. And again, if tests are your work too. So if you're going to take tests from somebody else, make sure that they get the credit. And I would suggest avoiding that, just because learning how to do tests or the exercise of sitting down and coming up with a bunch of tests is itself an invaluable learning experience. So please keep that in mind. Okay, questions, comments, issues, anything like that? All right. Good. I see, by the way, from the increased volume of bug reports and things that people have actually started on the project. That's good. It would have been nicer 2 weeks ago, but it's good. I'll take what I can get. All right. Okay, so last time I'd started on this journey of going through and looking at language features and asking what are how do they do that, and what are the implications for implementation. And from the idyllic Eden of early Fortran, where there was only one instance of a procedure active at a time, and where everything was a fixed size and so forth, we went to what happens when you add recursion to the mix, which now requires basically an infinite amount of space, an arbitrary, an unbounded amount of space for the local variables of any given procedure, because there might be any number of instances of that procedure active at a given time. And so the traditional data structure is the stack, and here is the stack in its simplest form, where we basically have the data that has to be that is specific to each instance, like where do you return to, what are my local variables, what are my arguments. These go onto this stack. Generally speaking, the arguments for the next call get computed as part of the frame of the caller. And exactly where this return address goes, whether you say it belongs to the caller or to the callee, well, that's somewhat a matter of taste, and it's not particularly important. But the important thing is that you have these frames that have this property. And you notice these two very thick arrows up there pointing to the left. These represent what typically on a typical machine, these represent the contents of registers that are dedicated to the purpose of keeping track of where the stack is. Now, for this particular instance, all we need is that top register because everything else, the top of stack, because everything else can be computed from it. Everything else is a constant distance away. Now, so in this particular case, we say that the frame size, now the frame size is the same, is a fixed distance for any given procedure. It's not the same, obviously, from one procedure to the next, the frame size might be rather different. Now what we can do at this point is, or the way that this works, is that we start by, suppose that F here, well, so the example that we're giving is F calls G from this particular situation. So at the moment we're in F, and we're calling G, and at this point, what happens is that that G allocates space for itself on the stack by decrementing the stack pointer. Yes, I know the stack is going up, but it does whatever it takes for the stack to go in this direction, upwards, which on many machines is decrementing the stack pointer, but sometimes it's incrementing the stack pointer. So it does whatever it needs to allocate that space. And then when it exits, and it knows how much space that is, it's a fixed amount, so that's easy. And when it exits, it just increments the stack pointer by that amount, and there you are. Increments the stack pointer, then you do something to pop off the return address and to branch to it. And that's it. That's it. Now, at that point, the caller can figure out what to do with those arguments that the caller placed on the stack. So the caller at that point can pop the arguments. There are other conventions where the callee pops the arguments, but it's easier, for various reasons, it's easier for the caller to do it, I think. So here is an example from the IA32. I think I took this from, I think I took this directly from GCC at one point. So here we have, the code for F. And F's code, first of all, decrements the stack pointer, so ESP, SP, stack pointer. We decrement the stack pointer by the 4 bytes that we need for F's single variable S there, single local variable. And we also we set that variable to 1, but the prologue, that is the part that deals with just the function entry and exit, is simply that first statement there. So this is just a loop, and you can go and figure out what it means. It's kind of fun, but you can see in this loop that when we reference y right here. So we're referencing y right here, y, checking to see whether it's greater than 0. So the way that we do that is that we compare, this is a literal 0, against the location of y. Now, y is in 12 off ESP. Now, why is that? Well, let's see. Initially, the stack pointer was, wait a minute, hang on. Let me see if this is actually an error. Interesting. I think that there's something wrong with this. No, okay. So y is at 12 off the ESP. This is because, if you think about it, at the moment after we do that decrement, the stack is pointing at, the stack pointer will be pointing at the variable S. Immediately above that will be the return address, And immediately above that will be the parameters, which are usually passed, which are in this particular architecture are passed in reverse order. And those of you who are familiar enough with C might realize why that is, actually. So that X is located at, will be located at 8 off the stack pointer, and Y will be located at 12 off the stack pointer. And that explains these offsets here, where it's loading stuff from a given offset from the stack pointer. Now, yes, I know you didn't, I guess you, unless they've started teaching IA32 and 61C, have they? No. Unless they've done that, of course, you have never seen this particular assembly language before, unless you've hacked the IA32. But you know, all assembly languages, the problem with assembly languages is that they're really all the same, except that unfortunately they were, the people who invented them weren't sensitive to this fact. And so they all had to be creative and come up with their own syntaxes for everything. And so you get these annoying variations. But this is GAS, the GNU assembler, and it's relatively straightforward. You can guess that these things are the operands, that these things are the operators, and that these things over here are the operands, and you can sort of guess that this might mean a base offset memory operation, memory operand. This thing in just plain parentheses is the same thing, except there's an implicit 0 in front. And you can sort of guess what these things mean. Jump means jump, means branch. Unlike the PDP-10, where jump meant don't jump, and skip meant don't skip. This one, it means something different. This is low defective address. Leal is low defective address, which means instead of calculate the address of the operand and put that in EAX, not the contents of ESP. And you can work through this. If you're interested in spending a happy hour, you can peruse the IA32 documentation that we have provided on the website. Okay. So this is what the things look like. And when we leave the function, then we come down here into the epilogue, where we first of all restore the stack pointer to where it was immediately after the call, and then we have this special instruction ret, whose purpose is to pop whatever on the stack and return to it. As you can guess from the fact that ret has no operands, the stack pointer is in fact a register. Is not just conventional. It's a register that the hardware in this particular machine knows about. Whereas on the MIPS, for example, it's not the hardware doesn't necessarily know that there is a stack. It just it's just how you use the thing. All right. So that was the simple case. Did I see a hand? Sorry. This is a simple case. Now let's go to a more difficult case. Now, in this, the case I just showed you suffices for a lot of things. For example, Java can do things that way. The reason that Java can do things that way is that even though you have things like lists and arrays and things like that, which can be of arbitrary size, and you can allocate those in Java. But what feature of Java is it that means that we don't have to worry about the fact that these have variable size? The very important feature, this is in fact a theme actually. There's a very important feature of Java. It means we don't have to, it doesn't screw up the previous picture for Java to have variables, local variables that have arbitrary size. And there's a reason for that. Why? What is the reason? Yeah. Garbage collection, that's, even without garbage collection, Java would not have this problem. Yeah. Yes, that's right. So everything is in fact of fixed size. When you see a variable that's of type array list in Java, it's not really that doesn't mean that if X is of type array list, that doesn't mean that X is an array list. It means that X contains a pointer to an array list. And it's this way. In Java, you can't do anything without having a pointer. Some of the Java supporters have said, no, Java doesn't have pointers, it has references. And then you look up, see what these mean, and you find that they are synonyms. Like that old sitcom in the 60s, Get Smart. They had this, not the craw, the craw. This is not the... So this is... sorry. I'm sorry, every now and then I get off on these tangents because one of my hobby horses is that there are a lot of people in my discipline who are extremely sloppy with their terminology, and they cause rampant confusion by silly things like saying that Java doesn't have pointers. On the other hand, there is a problem, there is a downside with that, which is that if you're going to do things that way, you need garbage collection. Garbage collection is not just a feature of Java that happens to be there. Garbage collection is an absolutely necessary feature of Java, because if you didn't have it, you would be in storage allocation hell. I mean, because you can't sneeze without creating 15 objects in Java. So you've got to do something about that. You've got to do something about cleaning them up. And it's really, for various reasons, if you've ever, now that you've had fiddled around in a language where you do have to worry about storage allocation, you might begin to have had a taste for how much pain that can cause. So Java actually really, so garbage collection is really an absolutely essential part of Java. If you don't have it, and then you want to avoid gratuitously creating pointers to putting things on the heap, which is not as cheap as putting things on the stack in general. So from a very early time in the development of programming, like modern programming languages, people have had to deal with this problem. So in Algol 60, and its earlier variant, Algol 58, which still survives, at least in the Air Force, in the form of a language called Jovial, Joule's own version of the International Algebraic Language, Jovial. You can allocate arrays, you can allocate local arrays of variable size. And they didn't want to put these on the heap, although they could have done that. Instead, they decided that they would try to put these things on the stack very often, or at least in many Algol 60 implementations. So how do you do that? Well, it's really not so bad. What you can do is, because the problem is that the compiler really wants to find things at fixed offsets, the answer is easy. We just sort of do the Java implementation behind the scenes. We have a pointer for this storage of variable size. The term unboxed, by the way, simply means that it is not explicitly on the heap. It's stored plain. So what we'll do is we will, behind the scenes, we will create a local pointer to this variable, to this storage, and we will reference, and in our code, we will reference through that local pointer. And therefore, since the pointer is a fixed size, and we put all the other fixed size together, we will be able to allocate to know where everything is relative to this second pointer down here, the frame pointer. And we can now, because stacks being stacks, we can put as much storage as we want on top of the stack like this, and everything will be fine. So we'll have everything we want. That is, we will be able to get at everything from fixed locations from this pointer here, and we will have as much storage as we need for putting for array allocation or whatever the variable size data is. So that's nice, but it does require all of a sudden that we keep track of this pointer. Whereas before we knew its position implicitly because the distance between here and here is fixed, we no longer know that because it will be a runtime quantity. So the convenient thing to do in this case is to keep track of this additional pointer so that we have both ends of the stack frame pointed to by something. Well, if you're going to do that, we now have a problem because, of course, that means you have to keep track of somewhere. You've got to keep track of where the what the distance of where your caller's frame pointer was. Because before, it's easy enough to just change, since I know where my frame pointer is, when I want to return from this function, it'll be easy enough to just move the top of stack down to here. But where do I move the frame pointer? How do I get the frame pointer of my caller? And the answer to this is that we introduce into our calling conventions another invisible behind-the-scenes variable called the dynamic link, which points to the frame pointer of the caller. So now, when F calls G, as we see here, when F calls G, G will save in addition to the return address, it will save this link to the place that F used to use for its frame pointer. So it looks like this. Here's the code. Oops, no, that isn't the code. The idea is that, I hope I have code here. Yes, here we go. So here's the code that you see. The difference from the previous slide was that we set up this dynamic link. So we save the value of the first thing we do is we save the frame pointer, for which the conventional register in the IA32 is EBP, the base pointer. I should say it's EBP when you're using 32-bit instructions, which you almost always are these days, or 64-bit. Then it's, well, whatever it is when it's 64-bit. So this means that we push the old address, then we push the new frame address, which is the stack pointer, the current stack pointer, into that register, and then we continue as before. When we return, we have this extra instruction that's on the leave, which is actually, I think it's actually a macro, as I recall. And this instruction undoes the first part. In other words, it pops the dynamic link into EBP. That's the purpose of the leave instruction. And then we return. So this extra instruction here and these two extra instructions up here, pushal and moval, take care of saving basically it's a linked list of the beginnings of the frames. So the frames are all linked together by these dynamic links, allowing us to restore order. Now, again, there are various reasons why you might want to do this, even if you have fixed size frames. For one thing, it makes all the frames uniform when you do that. They all have the same representation, and which makes it marginally easier to generate code. But it also makes it possible to make it easy, I should say, to write a general function that unwinds the stack, because you always know where the dynamic link is. It's always at a fixed location relative to the frame pointer, and so you can do a stack trace, or you can handle an exception or something like that with a simple generic piece of code that doesn't know much, but it knows where the dynamic links are, and so it can pop things off. Now you might consider what you would do how you would write such a procedure, such a general stack tracing or unwinding procedure, if you had a mixture of frames with dynamic links and without dynamic links. It can and has been done, and you might think about strategies that you would use to do that. And that are used to do that. Strategies basically that make life difficult for people like me who maintain debuggers, but which are interesting. Okay, so at this point we now allow you to have recursion. So we have a language that has recursion, and we have a language that allows you to put local data on the stack, so that it variable size local data on the stack, so that it will be automatically deallocated as soon as you leave. See, that's the big advantage here. No matter how much storage there is here, you deallocate it in one fell swoop when you move the stack pointer down to there. Right, so this is kind of neat. All right. And now things start to get hairy, because now we have to produce another special effect, which is that we now we're now in a language unlike C, but like, say, Pascal, actually, or Ada or GNU C, that allow you to have functions nested inside of other functions, or Python for that matter. Functions nested inside of other functions. So what's the problem with this? Well, there wouldn't be a problem except that these inner functions can access not just the variables can access variables in their callers sometimes, or in the surrounding functions. So, for example, in this case, we have G nested inside of F, and G is what is this? Is a recursive procedure, so it can call itself several times, and at some point down there, it accesses what is it? It accesses Y, which is a local variable inside F. And of course, at the point it does that, it could do that anywhere along the line. And so the question is, if I'm up here, if this is where my stack pointer is, and this is where my frame pointer is, and I ask for n, well, n is way down here, and in fact, this distance here can be arbitrary. There can be an arbitrary number of intervening g's in between. And so how do I deal with that? Not only could there be an arbitrary number of intervening g's, but things could get more complicated than that. But for the moment, let's just assume that we have this case where you call functions directly. There aren't any function values, which are another complication. But you call functions directly, and we want to be able to get at those non-local variables. If the variable is defined outside of all functions, it's easy, because then it's a global variable, it's static. You can put it in some fixed location, and you can go for it, no problem. But here we have a problem. So, the interesting thing about this is it's just an obvious feature. It's a feature that sort of falls out of language design. You say, well, I think I'll allow nested functions. Oh, that's nice. And it just happens that because of the scope rules, inside this nested function, you can access non-local variables. And so it's, from the language designer's point of view, it may look like a very simple thing to do, but from the implementer's point of view, it creates some problems. So how do we deal with this? Well, we need another kind of link. We need something that will, there are various ways of doing this. This is one implementation, all right, and we'll see another implementation in a bit. So what we do is we make sure that each nested function carries with it a link not just to the caller, the dynamic link to the caller that allows you to return, but also a static link to the instance to the activation frame for the function that encloses it. Okay? So, the term here, lexically enclosing environment. In other words, the function in this case, the function f, that has the function g defined inside it. And we keep track of where that is, And we basically pass that argument to G each time we call it, so that it will be able to, so it will know where to go for non-local variables. By the way, why do I only need to do it for the immediately enclosing function. In other words, I only need to store in G the pointer to F's frame. Why is that? Yeah. Right. Because I've got a linked list, basically. I can just follow the chain on up it. And I know, and because this is a lexical thing, it's a compile time thing, I know how many levels out I have to go to find any variable. I know that at compile time. It's all explicit. It's all right there in the text. So we now have three ways of accessing a variable. If it's a local variable, I just look at my frame pointer and find the variable, or maybe my stack pointer. If it's a global variable, outside variable, then I could just use the link time address, some fixed address. Or in the case of Java, I can use some. There are other ways that I can get at it, but it's some globally accessible address. And then if it's one of the intermediate things, that is, it's a local variable of some enclosing function, I just follow the static links up until I get to the appropriate frame for that function. So all you have to do, all right, so that's the design, and now it's just the job of the runtime of the compiler writer to make sure that the code in the function does that. Right? It maintains that data structure. So here's what it looks like. This is, again, the same thing as before where G has called, what is this? F has called G a few times, or F has called G a few times, and G now wants to get back at the appropriate frame in F. Okay, so how do we do that? Let's see, do I have, yes. So what I'm going to do here is for F and G, this is a somewhat complicated procedure, obviously, for which I show only some of the code. What F does when it finally calls G, and where is that? Let's see, it's somewhere in here. It calls F1. Yes. When it finally calls F1, it right here. It computes a static link and to its frame and pushes that or passes that in this special register here. In GCC, it uses ECX as the place to pass the static link. It passes that static link to the next function, and that function can then save it in a specific place and use it as it needs to. So that's the idea. We'll just if I am a function and I'm passing and I need to call another function, I know which static link that function needs, so I compute that. It's either the address of my frame, or it's the address of some enclosing frame. And I just compute that and pass it along. Okay, so that's very nice. And you should study this slide at your leisure, because it goes on and on and on. But and there's no point in going through all of this tedium. But you should be able to pick out from this the things that are maintaining this static link. By the way, you've seen this before. These static link things, you've seen them before, right? At a higher level. Where have you seen them before? What is always my answer to that question of where you've seen them? 61A. Yes, you've seen these before. These, yes? Yeah, they're parts. They're the little arrows that come out from the little arrows that come out from the one of the two bubbles in the double bubble things. These are the static links. Well, we'll see more of that as we go along. Okay, so there's a whole bunch of code. Yeesh, good grief, I didn't realize I had so much stuff here. All right, well, that's one way of doing it. I will show you now a second way of doing exactly the same thing, but a second and older way of doing exactly the same thing. But at this point, I think we should probably take a break. So, questions? Yes? Why are parameters passed in reverse order? Can anyone who knows C well enough suggest why parameters might be passed in reverse order? Yes? Why do you think? Yes. You can pass, in C it is possible, or C++, it's possible to pass arbitrary numbers of parameters to a function. And when you do that, although in principle, you'd think that they would have thought. I mean, it sort of emerged accidentally that you could do this sort of thing, because in the old days, you didn't even declare how many variables an externally linked function had in C, and so you could make it be any number, and it would be technically illegal, but nothing was checking it. So one of these strange situations. But when you have variable numbers of parameters, no information is passed as to how many there are. For reasons why that's still true, I don't know, but that's the way it was. So as a result, the callee has absolutely no way of knowing how many parameters there are. And if you push the parameters on in forward order, you'd have no way of knowing where the first parameter is. This way, at least, you know where the nth parameter is, because the first parameter is always at this fixed offset from your frame pointer, and it goes backwards from there. So you may not know where the last parameter is, but you know where the first parameter is. And in general, when you're accepting multiple parameters, you take them from left to right, and if there are extra parameters, then you just sort of ignore them, and this facilitates doing exactly that. So that's probably the reason that's become the convention, at least in anything where the calling conventions are dictated by C. Okay, let's take a break, and we'll start again in a few minutes. Yeah.
About something I was supposed to count. So you said that main is a symbol visible from built-in. I thought it was the other way around, that main was the root environment.
No. Main is sort of surrounded by. You think of main as being surrounded by built-in.
Surrounded by, so they're kind of at the same level.
Well, it's this happens whenever you've got this kind of. Ooh, what's this? Fluid dynamics. So, how do you explain things like imports and so forth? So here's my module, main or whatever, and I'm importing things into it. Well, there are various ways of explaining this. Now, the way that real Python does it, is that you get these local variables, which are either copies of the module contents if it's import from import, or they are pointers to the module itself if it's import module. But in the in the static sort of dialect that we do, and in static languages in general, you sort of explain imports by saying, well, it's just block structure, and the imported things are out here. So anything that's defined in here, then visible in here. And right, or something like some variation on that theme is the basic idea.
Okay, because the way we did the symbol table and we handle imports is basically doing what you said, statically replace the points to these environment. But for us, the root list, the root environment was main, and built-in was actually defined in main. So that's why I'm asking.
Well, I mean, I suppose you could put all the definitions for built-in.
Well, I have a special case for built-in where I just kind of keep a pointer to it, and when I'm doing searches, look into built-in.
I think you'll find it much easier to just say, here's main, and here's the environment pointer. It points to built-in, and that works. I mean,
okay.
And it explains why you can have a variable in main. It's the same as something in built-in because just block structure, it makes a local variable and all that sort of thing.
A variable or a function or class?
Same thing. I mean, it's if I have say true out here in our dialect anyway. So true is something I hear in built-in, and I define true. Okay, well that's fine. That just means that I now have a local definition of true inside main. Yeah.
What if you do?
The only exception to this is none. So you aren't allowed to do that. But that's a funny exception.
What if you do this for true in whatever?
That's fine.
That's fine.
That's a local variable.
That's a local variable.
Yeah.
But this is not fine. That's assignment.
Right, that's not fine because of that. It's not because of this.
If this didn't exist, say.
Right. If you didn't have it, that's right. If you did have this would be wrong because it's trying to assign to something that's been def. If you didn't have either of these, then it would be wrong because it would. If you didn't have either of these, it would be okay. It would introduce a new variable. Yeah.
Okay, that makes sense.
Yeah.
So in that case, I have to ask, when you do import from star, you kind of have this going on.
Uh-huh.
Whereas if you import from anything, you add to this symbol table.
Mm-hmm.
Whereas if you do just import module, then the module just.
If you import module, then the name of the module, name of the module is then available here, and but you have to access things by means of dot, so that's fine.
That's what we have. So it's just this.
Yep. Huh. Huh. Interesting. All right, let's get started. Again, if we might. So, the static links establishes basically a list of nested functions. Me, the function I'm nested inside, the function it's nested inside, and so forth. And as you know, sequences like that, sequences of things, have two major representations, linked list and array. Historically, this question of how do you deal with these nested definitions was solved first with an array, not with a list. It was solved I think Edsger Dijkstra is usually credited with the solution. In the implementation of Algol 60. Algol 60 also had nested functions. So he came up with the following idea. We will have a global array, a globally accessible array called the display. Another unfortunate term. You have to understand that this term display was invented before there were displays. And so we're stuck with it, sorry. All right, so the idea with the display is that I will save exactly the same list as implicitly you get with the chain of dynamic links, except, well, you get it backwards in that case. I will store this list forwards with the 0 element being the outermost frame and so forth. Or being, say, the outermost functions frame. Or I can have the 0 frame be the global scope, but that doesn't really matter. That isn't necessary. So I'll just store all of these frames in an array, or pointers to these frames, I should say, into an array. This array up here. And now when I have a bunch of calls, I will put an entry to that scope, to that frame, into the array at the position indicated by how deeply nested the function is. So things at this level, things at the level of def 0 that are not nested inside other functions, their frames will go in at location 0. Things like G1, or F1 and G1, which are nested inside a single function, their pointer will go in location 1 of this array. So the code is now actually pretty simple. Every time we enter a function that's at level n, or k, as I say here, I store its, when I finished computing its frame address, I put that frame address in global array or display sub k. And every time, and so I put it in K, and I also save whatever was previously there in my local storage, so that when I return, I just restore it from the local storage. Very simple. And it turns out that if you do this, and if you just do the normal calling thing, and all of your calls are to fixed functions, that is, they're all to names that have been defined by def, as opposed to function variables, then you will automatically maintain in each of these locations, you will maintain the appropriate base pointer, frame base pointer. Which means that accessing a variable at any level is a constant time operation. There's none of this deeply nested function, although you don't usually get them, so it doesn't really matter in practice, but there's none of this deeply nested function having to do a whole bunch of operations to find the address of its parent. It's all instantaneous. Well, not quite, but all constant time. And it works, and it also has another advantage, which is that if you don't have any functions nested inside you, if you don't have any functions nested inside you, then you can simply throw away all of the code to save and restore the display, because you're never going to use it. You're never going to have to use that particular entry. So you can just ignore it. Now, because you always restore a function, because you always restore the variable in the display that you set when you entered your function, that means that there's an invariant, which is that every time you return to a function, the display has not been changed. Right? So, which is a nice thing to remember. So you call a function, it changes the display, but then it changes it back. So you always get the same display back. Right, now this works, so all of this works, but if you think about it, you'll realize that it works only as long as and because we obey this nesting of function calls. Now everything gets screwed up, however. Here we go. So this is an example of where I'm calling. So F0 calls G1. G1 calls F1, I guess. Yes. F1 then calls F1 again. And as we do that, as we get each new F1, each new call of F1 or G1, you see that the display gets updated. Then F1 calls F2, that's more deeply nested, so F2's frame goes in position 2. It calls G2, let's say, so that happens. And when we finally get up here to the top where G2 then recursively calls G1, well, that then redoes the display like this, so that now accesses to G1's local variables will go to this latest activation of G1, just as they should. Right. And so here we have, this is the code for doing it. You can look at that at your leisure. All right. Now things become particularly interesting because everything has been easy so far. And the next step is, well, what happens? So far, I have not dealt with variables whose values are functions. And where have we seen that before? Yes, that's right. But that's another story for another day, so we'll cut it off here and leave things hanging.